Hi, my name is Adam Green. I am a member of the class of 2020 at Antioch College, and my major is a self-designed Bachelor of Science in Environmental Science and Ecological Economics. In this presentation, I'm going to talk a little bit about my senior project. My project investigates the relationships between socioeconomic and racial demographics and environmental degradation. We used a combination of GIS and statistical analyses to test a prominent hypothesis that inequality causes environmental degradation. We tested this in the state of Ohio using census and EPA data. Much of the work we reference in this study is rooted in environmental justice research. The academic field of environmental justice originated from the environmental social movements that followed the civil rights movements of the 60s. Dr. Robert Bullard was one of the first academics to work directly with environmental justice movements in his research. Bullard worked with a group protesting the disproportionate siting of solid waste facilities near black neighborhoods in Houston. Another highly influential publication in environmental justice came from the United Church of Christ's Commission for Racial Justice, who conducted a national study of toxic waste siting and concluded that waste sites were disproportionately sited near areas with high racial minority populations. Socioeconomic class was also a significant factor in siting, but much less impactful than race. Our study applies statistical research techniques used in environmental justice research to test a hypothesis posed in 1994 by James Boyce. The hypothesis argues that inequality can cause environmental degradation, and the amount of environmental degradation is directly related to how unequal the population is. Boyce is talking about inequality in the broadest sense here, not specifically about economic or racial inequality, but inequality in power and influence. Boyce defines two groups in relation to environmental degradation: the so-called winners of environmental degradation, in other words, those who conduct the activities and profit from it, and the losers, which refers to those who bear the non-monetary costs of the environmental degradation. These costs can be any effect of the degradation that is uncompensated, such as toxin exposure, soil erosion, destruction of public green space, etc. The losers have to pay costs of the activity without reaping any benefit. The winners of the degrading activity are incentivized to reduce costs as much as possible to maximize profits, which will typically also maximize environmental degradation, either by foregoing costly measures that reduce pollution in the case of production, or by depleting resources entirely in the case of extraction industries. The losers can try to limit or prevent the environmental degradation by reducing the economic incentive, either by paying to prevent the degradation or by making the degradation less profitable by defending rights in a legal system and requiring limits or protections. However, if a society has higher inequality, the losers will have less influence in economic injustice systems and will be less effective at preventing or reducing degrading activities. In this study, we test two hypotheses. First, we hypothesize that areas that have larger racial minority populations, higher high school dropout rates, and lower income are more likely to be subject to environmental degradation, based on the findings of previous environmental justice research. Secondly, we hypothesize that regions with greater inequality will be more likely to host environmentally degrading activities, as predicted in Boyce's hypothesis. To test our hypotheses, we use data from the EPA's Toxic Release Inventory, or TRI, as our metric for environmental degradation. The TRI logs every facility that releases toxic compounds like lead or nickel into the environment. TRI facilities are often industrial sites related to manufacturing, mining, electric power generation, waste disposal, etc. To measure demographic variables and inequality, we are using data from the U.S. Census American Community Survey from 2018. Our measures of inequality are Gini and entropy. Gini is a number between 0 and 1 that describes the distribution of wealth across a population, so we use it to measure economic inequality. Entropy is a measure of dissimilarity, which tells us how racially segregated a population is. We use this to approximate racial inequality. For our demographic data, we use measurements at the census tract level. Census tracts are the smallest geography recorded by the census, but we wanted to measure inequality at a larger geography because we thought that it would have a greater effect. So we used Gini and entropy data for the core-based statistical areas, or CBSAs, in Ohio, which are the metropolitan and micropolitan areas. Most of the tracts in Ohio fall under CBSAs, but not all of them. The picture you see here is an aerial photo of Cleveland, with the borders of the census tracts overlaid on top. This map doesn't contain the CBSA outline, but you can see how much the size of the tracts changes between downtown and the suburbs. This is because census tracts are based on population density. So urban tracts are very small, often smaller than neighborhoods, but rural tracts are very large and can almost be as large as counties. The red dots you see on the map are TRI facilities. We used GIS to add a binary variable to our tract data that defines the tract as either containing a TRI facility or not. This binary variable functioned as our dependent variable in all of our logistic regression models. We included the CBSA inequality data by using multi-level logistic regression models to see if the inequality of metropolitan and micropolitan areas affected the tract level outcomes. If this is the case, we would expect to see many tracts with TRI facilities in CBSAs that score high in Gini and entropy. As we hypothesized, tracts with higher rates of high school dropout and tracts with lower median income were more likely to contain TRI facilities. We found that Black population of tracts had different effects in different urban groups. To our surprise, there was a slight but significant decrease in likelihood of TRI facility presence in urban tracts with large Black populations. However, in rural tracts, there was a steep and significant increase in TRI likelihood with higher Black populations. None of our multi-level models improved the predictive power of our logistic regression models, so it seems based on these data that CBSA level inequality does not affect tract outcomes. This table shows the odds ratios of our independent variables from our logistic regression models. Odds ratios represent the odds of a particular outcome based on a given exposure. An odds ratio of less than 1 implies decreased likelihood of an outcome, while an odds ratio of more than 1 implies increased odds of a given outcome. In this case, the outcome is the presence of a TRI facility in the tract. Variables with odds ratios less than 1 are marked in red, while odds ratios greater than 1 are in blue. The lines on either side of the points represent the 95% confidence intervals, and the asterisks represent significance. Note how the percent Black variable has an odds ratio less than 1, but the interaction variable of percent Black and rural has the highest odds ratio. Our findings mostly confirm our first hypothesis, as we saw increased likelihood of TRI presence associated with tracts with lower median income and lower high school graduation rates. However, we we found that the effect of the black population of a tract differed between rural, suburban, and urban areas. This map on the right shows Ohio tracts shaded by black percentage of tract population. You can clearly see that much of rural Ohio is literally white, and that the black population of the state is highly geographically segregated in urban and suburban areas. Our multi-level models did not improve the predictive power of the logistic regression models, so we were unable to find evidence for Boyce's inequality hypothesis with these data. This could be due to a number of factors. Because the winners of environmentally degrading activities, those who profit, do not have to live near the environmental degradation, they may not even live in the same CBSA, and the inequality between the winners and the losers is then not captured by the inequality measures at the CBSA level. This hypothesis may be better tested at a larger geography, like comparing states or large cities or countries. This study could also benefit from a larger sample area, as there are only 57 CBSAs in Ohio, which is a small sample size, especially compared to the nearly 3,000 census tracts in the state. In this study, we found that lower educational attainment and lower median income in census tracts increases the likelihood of at least one TRI facility being in that tract, affirming the findings of previous environmental justice literature. However, we found that the effect of the size of the black population in a tract differed between urban groups. In rural tracts, a higher black population was associated with a large and significant increase in TRI presence, whereas in suburban and urban tracts, a higher black population was associated with a slight but significant decrease in TRI facility presence. We found that CBSA level economic inequality and racial segregation did not affect the likelihood of TRI presence within tracts. Thus, we were unable to prove Boyce's hypothesis at this geographic scale. This study had many limitations. One limitation was the use of census tracts. A better way to estimate exposure to hazards is by drawing radii of a consistent size, say 1 mile, around the points. This approach is commonly used when survey data is used for independent variables, as survey data can be processed as points in a GIS software, and those points will cleanly fall either within or outside a radius of a TRI facility. The inconsistent sizes of census tracts makes it difficult to assess exposure in a simple and accurate way. This study could be built upon by replicating with a larger sample geography or by studying larger geopolitical areas such as states and cities. Additional explanatory variables linked to inequality, such as voter participation, could also be tested in a multi-level model. I would like to thank Sean Payne for advising me on this paper and assisting with the study design and statistical analyses. Thank you also to all the faculty and staff putting together colloquia and hosting this presentation. Thank you for listening.